I'm going to spend a little bit over a half an hour just going through a quick background of how we've been using storytelling and metaphors to promote knowledge graphs. And just to give you a background, I work in a company where we have literally hundreds of different business units. And each of the business units make their own decisions about what new technology we use and what they use. So we have to work with them to explain these advanced technologies. And what we're finding is that if we can't explain it to non-technical people, they're not interested. So we're using a series of stories for non-programmers. These are finance people, marketing people, healthcare executives, to help them understand the value of these connected data sets. So the questions that we'll try to answer today is, what is storytelling? How does it help us explain things to a non-technical audience? The stories are really to illustrate the differences between connected knowledge graphs and the traditional relational databases. And we're going to talk a little bit about some use cases, and then we'll talk about how do we test these stories and how do we promote the idea of integrating AI with these things. So just to give you a quick background here, the way I approach these things is as a solution architect. And one of the things I try to introduce to people is that our job is to introduce you to a series of families of technologies. And we are not here to say that any one technology will solve all the problems. But what we are finding is that there's a new trend about using graph databases, or we call it highly connected data sets, to help solve big enterprise problems. So what is the role of the solution architect? The idea here is that if any business unit comes to us and says, gee, we need some help with this problem, we are going to come up with a series of ideas, and our goal is to be an unbiased matcher of their problems to the solution sets. We then take them through a very traditional process called architecture, trade-off, and analysis method, where we look at the quality attributes of what is important, what are their requirements. We look at our alternative approaches, and when we do analysis. And a lot of the work I'm doing is then, how do we fill in this box of the right things, and when is it appropriate to recommend connected data sets through graph technologies? So that's a lot of what I blog about, and a lot of the topics is how do we explain this to people. Now, one of the things that I have to mention is that I'm not the only person that's doing this. Hillary Mason, one of the most successful data scientists in her conference keynote in 2018, she mentioned that metaphors drive design decisions. How we decide things is often not the fact that we really have a deep understanding of how these integrated circuits work and how they optimize queries, but because we're given a series of stories to tell, and it is our job to make sure those stories accurately reflect the architecture, and that we create ways for people to remember those stories. Because most important is, when we're not in the room, what do people talk about? And if they mention the right stories, and if they use those appropriately, we can guide them to the right decisions. So just one of the things we always start off with is, remember, just because a technology is hot doesn't mean it's appropriate for everything. And you can see that graph databases are clearly the hottest technology around, and this is really taken from DB engines that harvest the web and find everybody that's talking about certain things. And you'll notice that graph technologies have really taken off in their popularity. The second thing to realize is that with this growing popularity, we're not going to be forced to use generic hardware. We're seeing this new generation of things called the hardware graph, where we're getting custom hardware to build these things. And this is a natural progression, right? We started out with these things called data lakes, the Hadoop ecosystems. We tried to integrate them together with these things called hubs. We realized that connecting them and allowing those to be queried makes sense. All of my blogging, I'm on EKG's Enterprise Knowledge Graphs for the last 2 years, have really been helping you guide yourself on the pathway so you can get to this hardware accelerated graph. And the hardware acceleration is just astounding. Just in the last couple of months, we've seen some incredible speed ups in hardware execution. So what does this really mean by hardware? Hardware today is optimized, a lot of the processors, to do generic processing. They're not designed just to do one thing and one thing well, and that is the pointer hopping that we use in graph traversal. Having custom integrated circuits that is optimized for this is going to give us a huge boost in performance. And this is not just about reducing instruction set. This is also about how we access memory patterns. The big trend here is to understand the fact that in AI, we've started out at the ground level of looking at images and looking at sound. And this is what we call very dense data. Dense data is data where our pixels, every pixel has data in it, and we load that into a GPU, and it's very efficient because it's using all of the data in memory. In healthcare and a lot of other things at the upper level of cognition, where we're not just classifying things, but we're trying to make connections, we have this problem called the sparse matrix, right? So if we took all of our patients and put them in one in each row, and then put a 1 in every ICD disease condition they have, you'd get this huge, massive matrix, but 99.999% of it is all zeros. So we need ways to efficiently manage data that has very sparse data, and that's why graph technologies are a logical choice. And I'm just going to give you 3 quick overviews of that, of things that have been happening. One is the fact that when a new patient comes into our emergency room or clinic or urgent care, we want to ask the question, have we seen a patient like this before? And of all those patients that are the most similar, take the 100 patients in the world that are most similar, what is the care path that we can suggest to get them better the quickest? What is the optimal recommendations, and what are the treatments? And so this is a very important thing that we do not overnight in a batch job, but right when the patient comes into the room. And what we realize through this is that we have to understand the idea that there are many things in knowledge graphs that are inherently serial, where every task that completes can't start the next task until that task is done. We call those serial graph algorithms. And what we're trying to move to this new era is called parallel graph, where we can instantly take a new condition and compare it with literally hundreds of millions of things in 50 milliseconds. And that's a much different challenge than we've seen in the past. All right, so how have we done this? We've done this by using standard parallel computation, such as an FPGA. Xilinx is a very popular distributor of that. And we've been able to hook up our graph databases, TigerGraph in this case. We create a user-defined function. We convert each patient to 32-bit integers. Those are called patient embeddings. Embeddings are a really big trend. And then we run it through this parallel hardware, and it comes out the top most similar patients in 28 milliseconds. So it shows you that we don't have to be slaves to the current processors that are given us. We can be very creative at doing these things. Another company that's making great headway is a UK company, GraphCore. GraphCore has realized that a lot of the performance benchmarks that companies are running in the past have been only working on dense. And what they're doing is building systems that work very, very well on sparse matrix and graph representation. That's the name graph in the name of the company. Core processors, massive amount of thread, 35,000 threads in each 1U device, and you can stack those devices to get a huge amount of parallel compute. And then just last month, this incredible paper out of Intel called the Intel Puma Unified Memory Architecture, where they'll be building custom chips just focused on graph traversal. So their goal is a 1,000-fold increase in performance. And that's really a story that has to be told. Anytime you can get 3 orders of magnitude faster performance, we want people to really remember that that's going to have a big impact on our enterprise knowledge graph analytics. So now the question is, what are the right use cases? So we're going to walk you through some stories that talk about the right use cases. Performance is obviously a big thing. Flexibility is another thing. And the one that's the hardest for people to get their heads around is this idea of using graphs to implement deterministic rules and to give recommendations and next best actions. So one of the things we found is that in order for our enterprise knowledge graphs to work, we do need an executive sponsor. This is often our chief executive officer that understands the strategic nature of real-time analytics. We've also found that getting our developers on board is also a critical step. But I have to tell you, after about 3 months working on graph databases, developers usually never want to go back to the old relational systems. What we have, the problem is in the middle. And remember, when you get a typical $1 million IT project running these days, you typically need to get 7 different layers of management to get consensus that this is the right direction to go. If any one of these people disagree, they will block your progress. And so these stories are really designed for these middle level managers that are not technical, but really want to understand why they should be doing this. So these retelling is something that has to be transmissible through not just one presentation, but you need to be able to give this to teams and allow those teams to then retell these stories to other teams while you're not in the room. And that means that you have to use memory devices to help them remember the key facts. The facts need to be based on the truth, but our storytelling is really designed for this viral nature of getting people on board. So I'm going to walk you through 4 metaphors quickly here. And these metaphors are really about storytelling in a fun and creative way so that people will remember this. The most important one, and the one that comes up the most, is called the neighborhood walk. And what this does is this helps people understand this idea of index-free adjacency. When 2 things in the real world are connected, make sure that there's a quick way to hop between those things. So let's go through the neighborhood walk. Let's say that you live in a house and you want to walk over to your neighbor's house. Well, how would you do that? Well, you'd walk out the front door, you'd point to that neighbor's house, and you'd walk there. And this is exactly the way that graph databases work. Everything that is related to other things have in-memory pointers. Now, we want to contrast that with the traditional relational databases that store atomic units as rows in tables, but they were never designed to join things together as quickly as a pointer hop. They added that feature on at the end when they took their COBOL flat files and they said, well, let's create some IDs and we'll compare all of those IDs in memory, and then we'll be able to traverse these things once all those IDs are compared. And every time we run a query, we have to recompare those IDs. Whereas graph is not like that. It's 1,000 times faster, and that typically means each core processor can traverse about 2 million edges per second, as long as those edges fit in RAM. And we'll talk about that in a little bit. So this is the definition, and I'm not even going to read it because nobody will remember this. It's too technical. We need a story that's compelling. So when we talk about this neighborhood walk, we talk about how quickly, in 30 seconds, you can walk over to a neighbor's house. And we can then model that in a graph. But let's compare this to how we would have to do this if the story was living in what we call relational land. Now, in relational land, you're not allowed to put a pointer in memory if 2 things are connected. You are forced. Imagine you walk out the front door and there's a big stop sign there, and the stop sign says, stop, you cannot go directly to your neighbor's house. You need to go downtown to this huge bureaucratic building called the Central Index. And imagine kind of like a big government center with long lines like the DMV, and you're going to be standing in line for hours and hours and hours. And you're never going to get to the front until you get to the front of the queue, and then you're going to say, gee, I need to go to my neighbor's house, and they say, what's the address? And you have to give it to them. Now it's 123 Main Street, and they enter it into their search index, and they start searching, and the more houses there are in your town, the longer those searches take. And they finally say, oh, okay, here's the longitude and latitude of that house, and then you're permitted to walk over to your neighbor's house. So what's the difference between these two? And the difference is roughly the difference between a pointer hop and a join, which is about 1,000-fold. And that means that it's going to take you about 8.5 hours to do this walk whenever you're trying to traverse relationships. So this story should be told in a funny way, in a humorous way, in a way that's going to make people remember. Remember, everybody hates standing in line for hours and hours. Remember the pain and suffering of do that. And if you can evoke that emotion, then you have a good chance of getting people to remember and tell this story. Oh, do you think we should be waiting for 3 orders of magnitude every time we do look at these relationships? And if not, then they can tell this story to themselves. All right, so that's our first story, neighborhood walk. Second story is what we call the knowledge triangle. And this isn't so much as a story as a way of thinking of the guru sitting on the mountaintop and all the knowledge that is accumulated and that wisdom is handled at that top level of knowledge. And as you go down deeper and deeper into the pyramid, you're going to get more binary ones and zeros, and you're going to have to spend a lot of time. So the question we really want to ask in this story is, how do we store knowledge? What is knowledge? How is it different from the raw data? Now, if you study these AI textbooks, here's a table of contents from the most popular book in artificial intelligence. You'll see that a huge amount of their work is on knowledge and reasoning. How do we store knowledge in a way that we can traverse it? How do we build ontologies and taxonomies? How do we store things in structured knowledge representation systems like SCOS? So those are all questions that AI has struggled with in the past. But now what we're doing is we're starting to say that instead of storing data at this low-level binary code data, which is typically what we see in a data lake, right? There's no semantic layer there. That's just the ones and zeros dumped from your operational source systems. What we're doing is when we assemble that data into things we understand, that's called information, the people, the places, and things, the concepts. We don't really make it usable until we tie those patterns together. And so this is often called the DIKW pyramid, or we just call it the knowledge triangle, because we don't spend a lot of time talking about knowledge at the top. Wisdom is really how do you store knowledge in a way that's transferable between systems? How do you make a single representation of the truth so that all your business units can do that? It's really a higher level of how do we store knowledge to make it accessible across multiple systems. So the challenge we have about this story is that we have to also make sure that it talks about the productivity of our people who are analyzing this data. And if you take a look at the typical customer satisfaction of the data lakes today, they're not very happy because each of them have to write separate ways to access this data. We have hundreds of data scientists where I work, not thousands. They each have their own libraries to make sense of this, and they say 80% of the time that they spend is just the data engineering, getting all this data, connecting it together for each project. Only about 20% of their real work is actually data science, building the models and testing those models. So what we're starting to see now is that we are moving from this idea of the data swamp into this highly rich area of knowledge graphs, and we're going to be using AI to continuously harvest this low-level data for patterns and connect those things together. And the idea then is we'll then get to the stage of reusable wisdom. So there's a couple other, and I'm not going to spend quite as much time on these. One is called the open world assumption, where we say that anybody should be able to add any data at any time. I should say that we're borrowing this term from the semantic web, where they have a closed and open world, but we're really focusing on the idea that anybody should be able to add new data to the graph at any time without breaking existing queries. And the idea here is we want to often build either a fixed schema or agnostic schema. And there's different trade-offs for doing that. SQL databases all have fixed schemas. Some graph databases are schema agnostic, and some allow us to do validation, and we can use rules like shackle to validate those data, optionally validating those data on top of our knowledge graphs. So the key thing is, in the past, when we had these relational databases, we weren't allowed to add new data to these things without going through a long, involved approval process. And the reason was that if we changed the structures, all of those SQL queries might break. So we're trying to go to this new world where anybody can add anything as long as that model does in fact reflect truth, reflects the real world. There's another pattern we call the Jenga tower. And the Jenga tower says, what is the stability of your queries over time? And the idea here is that little block at the bottom of this tower is like a new attribute that you want to add to a relationship. And anybody should be able to add that. But the problem in the past is we had to often refactor all of our code when we wanted to make a small change in the data model. So the real question is, how do we change the way we build things so that our query pools are stable? And one of that things is that we have a focus on data modeling. We try to model the world correctly, the model of truth, and we don't worry about optimization of a join anymore. We focus on a single model of the truth that everybody can use. Why is this important? In the past, we've done a lot of research on the stability of SQL and Spark queries. We found that as we changed the model, we couldn't hold up. And that's why LPG and labeled property graph models really are taking off, as one of the reasons that they're taking off, because of the stability of these systems. Okay, so that's kind of some of the basic stories. I'm going to take you through a few other ones because integration with a lot of the AI systems are much more interest for people. My blog has a lot of these other stories, and I'm not going to go through them too much because often they're really focused on a certain area. But one of the stories I want to go through is this idea of explainability and why knowledge graphs help us with this explainability. And here's the way the story goes. There's this bar in your neighborhood called Deep Learning Bar, and they have this deep learning bartender. And the bartender has a reputation for recommending really good drinks. So you go into the bar and you say, hey, I'd like to have a drink. And the bartender says, oh, that's great. And he looks at you up and down. The robot says, from the looks at you, I would say that you would like a Guinness. And you say, wow, that's amazing. That's my favorite drink. How did you know I'd like a Guinness? And the bartender looks at you and says, I have no idea. Right? And that's the idea here is you can recommend something, but you can't explain it with deep learning. Right? We have these very, very deep neural networks, but they all are abstract mathematics and they have no semantics. They have no meaning in the real world. And that's the thing that we can bring together when we bring the right marriage of knowledge graphs, where we use machine learning to build these concepts and the relationships and their connections. But when we make a recommendation, we can traverse those graphs, we can traverse the concepts, and we can build an explainable letter so that we can explain to our constituents why we've made a certain recommendation. So how does this really work? In the original way that we did these things, we took a lot of our training data, we built these machine learning process, and we learned the functions, and we would then just give a recommendation to our physicians. For example, we think that patient XYZ should take drug 1, 2, 3, and that would be the optimal thing. But we couldn't explain why we made that recommendation, other than, well, it's based on analyzing hundreds of millions of patient records, right? What we're trying to do is get to this new era where we put an explainable graph model in between the machine learning process and then explanation interface. And that means that as we traverse this, we're building a document and we can explain why. We can tell you what our confidence levels, we can help engender that trust, and we can even give links to references to papers that justify this, and to data sets and to reports. Right? So that's why we're really focusing on bringing this holistic approach to having AI and machine learning feed our graph, and that graph has data and concepts that everybody can understand and we can build explanations on. So a couple things just to mention, cautionary tales here. The first is that our brains are kind of like graphs. Our brains typically have about 84 billion neurons, but these neurons are also much more highly connected, typically about 10,000 connections per neuron, whereas our knowledge graphs that we're building at scale almost consistently have a 5.2 relationships per vertex, so a much, much lower degree a much smaller number of connections between vertex. So we want you to be very cautious about using these metaphors because the brain structure is in fact very different. Another story I wanted to relate is this idea that when people say, well, we have to use AI and deep learning and machine learning for everything, we want to make sure that you realize that just like our eyes see only superficial patterns but may not understand things, that's really where a lot of machine learning for images really are today. And one of the things I do in my student classes where we're teaching AI to junior high and high school students is we're taking these 3D printed models of a turtle, for example, and we just literally tape a wood grain texture to the top of that, and we put it in front of our cameras that are doing object recognition, and they think it's a rifle, right? Because the training sets were never really based on turtles that had wood grain, right? It's something that they're really focusing on the texture of something, but not on its shape and not on its structure. So it's really important to understand that current AI is not really at the high level of cognition. It doesn't really understand these things and shape. It's not building a scene graph of these things. It's really focusing on patterns and that low-level pattern recognition. And so now one of the things we want to just mention is that when we're looking for algorithms that work against graphs, one of the tragedies that in the past we haven't done is we haven't taken the structure of the graph into account when we're building features for machine learning. And one of the summaries I have is structure is the new gold in data mining. So we're now taking algorithms like graph convolutional neural networks. There's a whole presentations we have on that separate topic, graph embeddings, and we're finding that structure helps us find deep insights. There's a lot of interesting things that came out from this 2018 paper and from Google, and that really shows you how Google is really pushing the boundaries of using labeled property graphs in their system to find deep insights, not just for search, but for other areas in Google Health. Don't think I'm going to go into this in too much detail, just to say that we're treating graph data, think of it as an image as a Cartesian plane where there's Euclidean geometries where points have consistently distance, and we're just throwing out the assumption that points have to be equidistant. Every relationship in our graph is a different structure. These are called non-Euclidean geometries, and we're still using the same kind of neural networks to do classification and things like that on those graphs. So these are all coming out of those papers. One thing about this is we can build also hybrid layers where we classify things by images and then find these embeddings, make sure those embeddings are structured, and then we can process those in parallel. So to summarize here, we're really going through this era of computing where we started out with procedural rules, where we wrote if then else statements as rules, and we wrote those in programs that access the data, and we came up with answers and explanations. The machine learning era said, let's still ask questions, but let's pair the data and the questions together and predict the results. But we had to go through 10 million weights, and there's no explainability when we just use pure machine learning. What we're really trying to move towards is this graph era. The graph era is where we're still using both knowledge graph and machine learning together so that we can combine knowledge and answers, but also create explanations for our stakeholders. Not everybody needs explanations and trust, but in healthcare and a lot of other areas where we're recommending things to customers, those answers are really important. So those are some of the stories. Couple things about storytelling: it's testable. We encourage everybody to present stories face-to-face, gauge people's reactions. That's harder to do in the COVID era, but we're definitely want to make sure that you test these stories, get back to people about 2 weeks after, and then see if they can answer the questions back. What was this thing about graph? How is it different from relational? What was that neighborhood walk story? Could you remember that story? If they can't remember it 2 weeks later, you need to go back and work on your stories. Storytelling is testable, and we encourage you to continue to test that until you have stories in your context of your groups that do that. All right, so I think I'm just about at time here. I just want to encourage people to reach out to me if you have any questions. I blog on Medium. Share your stories. And there are just a couple other things. Just to remember that when we think about graphs, system thinking is really an important part of that process. That we want to make sure that we understand that graphs help you think about different ways of solving problems and interconnecting these parts. We feel that connected data is the key to modern data science, and our data scientists all agree to that. We want you to start to thinking of your projects not as silos, but interconnected graphs. We hope that you understand that connecting data adds value, and trying to put a cost on that is difficult because it's based on your insights. So understanding what is easy to measure and what is hard to measure doesn't mean you shouldn't try to measure those insights. It means that you should start to put abstract processes in place. Remember, these laws are absolutely going to be prevalent forever. They're not going to change. And we hope that you have some good, inspiring questions to ask them. Okay. Should we open it up for questions?
Great. Thanks, Dan. Fantastic talk. Great feedback on the chat. Question from Jakob. Expanding on the idea of telling stories to promote graph use, how do you facilitate conversations around schema development?
Yeah, great question. Schema development is really kind of one of the things that shows the maturity of your graph analytics team. One of the things that I have run across over and over again is that when people often are starting out, they model the graphs like relational. They attempt to minimize join operations, and they don't really try to find the connections that model the truth. And so it's really important that you try to unlearn the habits that you have, and that we hope that everything that a lot of the users can go beyond that and really model the detailed relationships as they should be.
I'll read this question from Jean.
Okay.
So, do you think application developers must create applications interacting directly with graph DBs instead of relational DBs? Or should applications still manage relational data, assuming that data are later transformed, exposed, or dropped into a graph database?
Great question. So I think it all depends on context, of course. It's kind of a cop-out to say it depends, but that's really the first answer. But the way I would refine that is when you are creating integrated views of your enterprise, specifically all the touch points from your customers, the relational databases just don't scale. So if you're focusing on those integrated analytical views, it should always be in a graph. If, on the other hand, your focus is compatibility with existing relational systems, then you're going to make a different set of choices. And that set of choices is going to be based on how much data you have. Is it third party? Do you have the ability to change it? There are organizations that are using graph databases for full ACID transaction stores, single source of truth, things like that. But that's a different set of patterns. So I think the answer really depends on the context and which patterns are appropriate for your group.
As usual, the answers are dependent on the context. That's kind of the big rule about graphs and reality. So we have another question here. And Jakob, there's a lot of people that can weigh in on this, but he's asking if there are tools for schema development.
Oh, tools for schema development.
Yeah.
most graph databases have graph modeling tools. There are a handful, I'd say about a dozen of other third-party tools that you can do modeling with. And a lot of them are very graphical oriented. They use web browsers. So I'd say yes, there is a group of tools, and I should mention there's some people that keep a list of all those tools. And I'll if you give me a time to think of that, I will try to remember some of the people that are keeping a list of those tools. But yes, there are other tools that you can use to do graph modeling, and then they generate the data definition language for those graphs for Cipher or Tiger Graph or whatever your graph databases are.
I will definitely follow up with you about that list, Dan. That's fantastic news. Okay. And we have another question from Matei Moore on storytelling. Along with your blog, Dan's blog, what resources do you recommend for learning and practicing storytelling, especially for decision makers?
Great question. There is a really good book by Alan Alda on the processes he's gone to help scientists communicate with their constituents better. And it's something like the title of, "If I had this look on my face, would I understand you?" Something like that. And I'll get the link to that book too. It's a very short paperback book. It's not a huge read, but it really does go into some of the brain science behind storytelling and how you can use emotion to get people to remember. And Alan Alda is the champion of comedy, of course, and one of the ways that he is teaching people to do this is by improv, right? You go to improv and you get people to laugh. And if you're talking about a topic and you can trigger laughter, you're going to get them to remember those things. So those are very good books. I can give you a handful of other books that I found useful in the past too, and we can post that on a resource site later on.
Great, yeah, and I can share that in the Slack as well. And I can attest the power of laughter and Dan's storytelling. We had a Knowledge Espresso about a month ago, I think, and I still remember the story that you used to tell us about graph embeddings, which was
what was it, Ellie? Tell me.
Yeah, Mowgli facing an orange cat, and we weren't sure if it was a house cat or a tiger, and I laughed because I have an orange cat. So,
so we made an emotional connection in that moment. And now here's the hard part. Can you tell me what was the take-home point about that story?
Yes, I can actually, but only because I think about this all the time. And because you're such a great storyteller. So the idea here was, how do we actually help the computer, the AI, recognize the difference between a threat, which would be the tiger, and the house cat? And that was really the point of graph embeddings as a solution.
Right. It's a speed thing, right? If you can't recognize that tiger in a fraction of a second and turn around and run back to the safety of the village, your life will be in danger. And it's the same thing as if you're running an e-commerce site and you're recommending flamethrowers to people that are trying to shop for wedding gifts or baby gifts. Your e-commerce recommendation is going to be endangering your existence too. So you're right, it's all about real-time recommendation, and I'm glad you remembered that. So the story was successful, I guess.
Oh, absolutely, yes. The entire coffee chat was, and I'll share the link to that as well. So I think we're a little bit past time, but Dan, wonderful presentation. It's so great to see you again.